but the paper will be other. I hope I will. No, because the presentation is approving. Okay. Okay.
Is this one?
Yes.
Okay, perfect.
Thank you. So,
Okay.
please start.
Well, thank you very much for the introduction. I start again. So that's what I will present as part of the PhD work of Paul Hoffmann, who was supervised by Melanie, Todt, and myself. We are from Institute of Lightweight Design and Structural Biomechanics in Vienna. And that's a collaboration with Infineon Technologies in Austria. And the work was funded by the Austrian Research Promotion Energy Agency. And this work is already been published in the International Journal of Fatigue, which you can see here. Again, it's about thermo-mechanical fatigue modeling and the influence of material parameter calibration. Looks similar, but the approach is a different one than before. Again, microelectronic test devices under thermomechanical fatigue. This means we have a silicon substrate with a metallization layer on top. This is subjected to thermomechanical loading, and we look at the fatigue damage accumulation, but now on the crack pattern on the surface of the copper. So we do not look at the cross section, but now we look on the crack pattern on the surface, which is visible. Approach, there is production of the test device by Infineon. They do experimental fatigue testing and image analysis of this crack pattern, and our task is the modeling and simulation of low cycle fatigue. Again, Hoffmann type fatigue law. Now in this case without continuum damage mechanics, just the lifetime to onset. And again, parameter calibration. The goal is to develop predictive tools in the reliability assessment in microelectronics. So I will show you the test under device, the damage detection by image analysis, modeling and simulation, and calibration and application. So the device under test, here you'll see a cross-section of a symmetric test design. Let's start with the right-hand figure. It's called design B. It's symmetric here on the right-hand side. You see silicon, the gray part, which is much thicker than shown here, so that's silicon. And close on top there is a copper layer. So the copper layer is about 30 micrometers, and the silicon is about 200 micrometers or more. But close to the interface, there is this red area that's called polysilicon, and this mimics the power generation. So Infineon can produce this on purpose, and it has the same features than thermomechanically than a real chip, but it's much cheaper. So the red line here is the power dissipation, the heat sources. So that's design B. Design A on the left-hand side is the same idea, but you see here that the polysilicon doesn't go until the center, and with an additional layer which causes a small step on this position. So we have geometrical features and inhomogeneous power distribution, so to speak, in design A. Doesn't work anymore?
Here is the presentation.
Okay.
Wait. Maybe I will close this.
I cannot.
Because
Do I switch the other presentation? Now it's working. Okay.
Okay.
Yeah, thank you.
this is other presentation.
So I was computing on the other. Okay. Now I have only two presentations. Not three.
Yes.
Okay. So two different designs. What pulses are applied. You see here the voltage which is switched on this polysilicon. You see the power dissipation, and here you see the temperature rise close to the interface between silicon and copper. And this pulse takes 200 microseconds, and it is repeated every second. So there's a lot of time to cool down and to distribute the heat. The base temperature from which we start is 100 degrees centigrade, and the maximum temperature in the device is about 450, and at the long cooling time it goes back down to 100 degrees centigrade. And this will be done for 500 seconds. So it's a severe overload pulse. It's not a service condition, that's really a pulsation which is intentionally that high to have damage in the device. So damage detection by image analysis, we look on the top of the copper surface, and you see some damage crack pattern here developing. So that's an electron microscopy image. It's binarized. That's the result of the binarization. And then we simply count along the coordinate C. On one pixel row, we just count the number of cracked particles or of registered particles. And if you do this for every location, we get this pattern which looks like this. So you see clear the symmetry here, and you see that this is a not even distribution. Remember, there was some no power dissipation in the center, and there was some additional steps on. So that's the raw data from the image analysis. What do we do in modeling? So we do finite element modeling. We have the initial geometry, properties, everything. Then we run a transient thermal analysis to get the temperature field over time as a spatial distribution. And these nodal temperatures are then again given as boundary condition to a elastoplastic analysis. We look for the stabilized cycle, and if we have this, we can compute the fatigue indicator parameter. So this is, I will show you next one figure of the nodal temperature distribution and the distribution of the fatigue indicator parameter. So that's the temperature. On the bottom you see the entire device. You see a strong gradient of temperature in the silicon because the conductivity is lower, and you see heating up in the copper. And if we zoom in into the copper layer, it looks like this. We have highest temperature in this region and lower temperature towards the symmetry. That's design A, which is the more complicated. And this is taken in the event where the maximum temperature occurs in this device. So that's the input to the elastoplastic modeling. And with this, again, with the Fatemi-Sossi fatigue indicator, the most important influence is the shear strain range and the critical plane approach. So if we look here on top, we have design A. We see that we have some gradient in the fatigue indicator, but it's not very strong. So along the surface here, that's quite evenly distributed, at least in this region. In design B, it's even more uniform. If you would see, yeah, that's design B. So we can compute this, and we get some numbers. We get some numbers of registered pixels, and we get some numbers of the fatigue indicator, and they need now to be made comparable for calibration. So what do we have from the experiment? We have 2 samples of each design. Since they are symmetric, we have 4 equal configurations, so we can at least do some statistics. From the simulation, we have this fatigue indicator parameter distribution, but we do not know what is a critical value now. And we consider this then now in terms of a Coffin-Manson low cycle fatigue approach. And we consider now the design A. And the interesting thing here, or the good thing is, we have an experiment where we have locally different loading situations. So we have one experiment which gives us, let's say, different points in the fatigue curve. That's a nice thing. So left design A, the grayscale is all the registered, the raw data of these 4 devices, and to flatten this out, we take the move mean over 250 data points, and the move mean gives us this flattened curve, and similar for design B. So to get out the noise. Second, we have the fatigue indicator parameter, and if we plot the fatigue indicator parameter on the top surface of design A, you see this characteristic hump here. It's qualitatively similar to what we see on the surface cracks, on the crack density, and in addition, in the indicator, we see here also this effect, which comes from this small step on the copper surface. So we have actually here 2 effects. This is a geometrical one, kind of a notch, and this is coming mainly from the temperature of the device. So we want to make this comparable, so we need to do some normalization. As I said, we do this for design A, and for the experimental fatigue, we just normalize this to the maximum of the move mean to set it somewhere. So that's the experimental damage, which is normalized to the maximum of the move mean. In the simulations, we have this Coffey-Manson type law. That's the fatigue indicator parameter, and we interpret this as a low cycle fatigue curve. And now, here we have damage, and here we have number of cycles. So if we want to normalize the Coffey-Manson law, we have to normalize, so higher, this goes from 0 to 1, and this goes from 1 to 5,000. So we have to take the inverse of this. We take the minimum of the move mean over the number of cycles. So that's formally written there. And instead of the number of cycles, we can plug in this equation, and we get the fatigue indicator parameter to the power of 1 over this fatigue exponent. So what's now the value of this fatigue exponent? You see here again the gray. This is now the mean over the 4 different experimental results. So the noise is reduced because of the mean, but it's still there. And you see 4 different curves for different values of this exponent. So depending on the exponent, you can shift up and down, or well, not shift, you can bend it more. They are all hinged on this point because this was the point where we have normalized those. But you can change the influence of the lifetime. And we do a least square estimation of these values, and it turns out that the exponent of minus 0.35 has the best fit, somewhere between the dotted and the dashed line. So we can fit the exponent. Second is to calibrate the factor. Sorry for the typo, it's not the exponent, it's the factor, gamma prime before n. We do this under the assumption that 5,000 is some critical value. So that's, let's say, relative. We just assume 5,000 is failure. So the industry partner tells us if the crack pattern is like this, we consider this as failure. And if we consider this as failure, we can also calibrate this gamma, which is 0.14, and this is done in the sense of a relative lifetime calibration to reach the same state of surface damage. Then we will compare this again, the mean over the 4 experiments. Again, still for design A, we have here our fitted Coffin-Manson law with the two parameters. You see it follows the trend quite nice. So the maximum here, also this reduced damage or increased lifetime in the lower temperature area. And we can even see in the experiments the effect on this step here. We didn't take into account this local step in the normalization because we wanted to get rid of this, but still it remains here as a markable feature. And on top we have here the dashed line is the surface temperature which occurs. So then we can apply the same calibrated material to design B. It's the simpler one, it also fits, and you see that if we have 5,000 cycle on design B, we are, let's say, beyond lifetime, so the damage is a little bit larger than that. So design B would last less long. Okay, thermomechanical fatigue on a metallization layer on a silicon substrate. As typically in microelectronics. Colleagues did sample production with special features on purpose. It was put to overload pulses in the experiments, and from the surface crack pattern image analysis was done. And on the modeling side, we have the low cycle fatigue modeling and simulation tools. And we did some statistical evaluation of our predictions and of the image analysis. And finally, we could calibrate the parameters for fatigue simulations, at least for some relative lifetime estimations. And again, the goal is to provide the industry partner with predictive tools for reliability predictions. Thank you very much.
Thank you for that. Now it's time for some question. Please.
Yeah, very interesting work actually. So it wasn't exactly clear to me that it's a modeling. Is that 3D or do you have a 2D model? And do you calculate this FIP parameter like somewhere in the layer, or do you also calculate at the top surface where you also do the experimental SEM imaging?
So the FEM model is a plane strain model. We do not have a gradient in the thickness direction in the geometry, and the part which gets hot is very small compared to the entire thickness of the silicon. So the better part of the silicon just stays cold and restrains the strain in our region of interest. So that's the reason why we use plane strain. And in the fatigue indicator parameter is computed in every element. So we have here something like 20, 30 elements in the thickness. And for every element we compute this fatigue indicator parameter. On top I have to say the fatigue indicator parameter is based on triaxial strain tensors. So since we have plane strain, we also have mechanical strains. Total strain is plane, but the mechanical strain is also out of plane. And the implementation we have is for full three triaxial strain states. And it may happen that the critical plane is also inclined with respect to the.
And then in the experiments, I guess that it's sort of like a region that you heat up, but do you take on board all of the data, or do you exclude like sort of like the outside region?
Yeah,
only take on board to the region that basically corresponds to the plane strain assumption of your.
No. Well, in the modeling we exclude this region because we have influence of this, which is stress singularity. So that's a nightmare. That's the full device in the yellow line. And we just neglect this small layer around.
But that's only on the right and left side, but not on the top and bottom. You don't see any influence of the fact that it's finite.
So what you saw before, the model is a cross section here.
Yeah, I understand. Yeah.
And that's the entire device, and some you need power supply, whatever. But in this region, we have in design B, we have quite uniform situation. and in design A, there is the center, there's the leg of this heating, and we take out a little bit smaller. So but you see the influence from the border, because there is less heating.
That's also why there's a slight mismatch on the border, right? But
yes, you're right. So in this region it didn't fit well, but our interest was more on this typical shape. And in addition, this geometrical feature.
Nice.
Thank you for your presentation. So maybe I didn't hear it clearly, but how the temperature affected the fatigue degradation in your simulation model?
Only by inducing mechanical stresses and strains.
Okay.
So that we have a temperature field, and this temperature field over spatial and temporal over time is just applied as a boundary condition that it's pulsating.
Okay.
And this gives the
So
elastoplastic simulation.
Okay, so first you run the thermo-mechanical analysis and get the stress and the strain output to drive the fatigue model rate.
We run it sequentially coupled. We do the thermal analysis before,
Yes, yes.
and then we do later the elastoplastic simulation. And the elastoplastic simulation gives basically this.
What does gamma mean?
Gamma is the shear strain.
Okay,
So that's the Fatemi-Sosi fatigue indicator.
okay,
Delta gamma is the strain range of the shear strain, and this is combined with a critical plane approach. So we just take plane after plane and we look at what is the maximum shear,
okay.
what's the shear range in this plane, which is actually not a trivial problem in 3D Tscharnuter case.
Okay, thank you.
Thank you very much. Second slide. Now we have that presentation. I'm chairman, but also a co-author of this paper, and I will start. Yes, beginning is by me, but the finish.
Only don't go big presentation, which is the pointer?
Yeah. Okay. I will start, as I thought, this